Hi everyone, it's Mrs. Jennison here. Welcome to our lesson on chromatography. As with all of our lessons, it would be really useful if you had a pen or a pencil and a piece of paper handy so that you could work through the activities with us. Today it would also be useful if you had a calculator so that you could use it for some of the calculations that come up in this lesson. Our challenge today is to be able to explain how chromatography separates a mixture of chemicals. Our aspire is to be able to analyse data from paper chromatography to identify chemicals in a mixture and to calculate RF values. So the first question you might be asking is, what is chromatography? Chromatography is a technique which can be used to separate a mixture. Here is an example of what a chromatograph, which is the results that we get from chromatography, could look like. As you can see, the mixture is made up of three constituents, A, B and C, and they have travelled different distances up that paper. Now, how does it work? Essentially, all methods of chromatography involve a stationary phase and a mobile phase. The mobile phase moves through the stationary phase, taking with it components of the mixture. Each component will have a different attraction to the mobile phase, so will be carried a different distance through the stationary phase. Now, the most common example you will see is a paper chromatography, and it is actually one of your required practicals. However, I will show you a little video on how it is set up. So following that video and that information, I've got a few questions that I'd like you to have a go at. The first one, how is chromatography carried out? That's a description of the method that you saw in the clip. Then what is the mobile phase in that example, and what is the stationary phase in that example? In the image, which colour had the strongest attraction to the mobile phase, and how can you tell that from that image? So you should have something like this. A drop of the substance is placed on chromatography paper onto a pencil line. This paper is then placed into the solvent. The solvent moves up the paper and carries the substances in the mixture with it, so we can compare this with a known chromatogram. Now it's really important that the line is drawn in pencil, because if you drew it in ink, the line would run. The mobile phase was water in that case, or it is a solvent. The stationary phase in that example was the paper. And in the image, yellow had the strongest attraction to the mobile phase. We can tell that because it travelled the furthest distance up the stationary phase. Once we have a chromatogram, we quite frequently calculate RF values, essentially so that we can compare our results to other people's, regardless of the size of their piece of paper, because we can't guarantee that it would be the exact same size piece of paper. So to calculate an RF value, you measure the distance moved by the substance, so by the spot that you are looking at, and you divide that by the distance moved by the solvent. So from that start line to the solvent front, which is the distance where the solvent stopped. In an exam, you could be asked to measure that, but for today, I am going to give you the values to make the calculation, because depending on your device, you would have different measurements. So, the example. So this is our first one. We can see on the diagram that the sample travelled 2.5 centimetres and the solvent travelled 5 centimetres. Now, using that equation, RF equals distance travelled by the substance divided by distance travelled by the solvent, that would give me 2.5 divided by 5, which gives me an RF value of 0.5. There are no units on RF values. So, using the setup that I've just shown you in the last one, what I'd like you to do is I'd like you to calculate the RF values for each of the pigments in that chromatogram seen on screen. So you will have a separate value for blue, purple and yellow. So you should have, for blue, the RF value is 0.8. For purple, it's 0.6. And for yellow, it's 0.2. Let's have a go at one more. So I'd like you to calculate the RF value of the blue dye. So you should have 0.4. So now it's time for us to have a look at what this would look like on an exam question. Chromatography can be used to separate components of a mixture. A student used paper chromatography to analyse black food colouring, and the chromatogram in the diagram shows the student's results. What do the results tell you about the composition of the black food colouring? We've been given some measurements. So the distance from the start line to the solvent front is 45 millimetres, and the distance moved by food colour C was 18 millimetres. We'd like you to calculate the RF value for food colouring C. Table 2 gives you the results of chromatography experiments that were carried out on some known food colours using the same solvent as the students. So we've got 4 different food colourings, the distances involved from the start line to the solvent front and by the food colouring, and then the RF values for those food colourings. Which of the food colours in Table 2 could be the food colour C from the chromatogram? Give the reason for your answer. So now it's time to check our answers. The black food colouring in part A contained food colourings A and E, but there was actually 3 spots, which means there was also one other unknown substance. The RF value was 18 divided by 25, which would have given you an RF value of 0.4 or 0.40. The food colouring from the table that it could have been was fast red because they had the same RF value. So that's everything from me this lesson. I will see you in the next one.